Progress.
All right. What's your name?
Muskan.
Okay, Muskan. So you were not here last time, right?
Yes.
Is everything okay?
Yeah.
Yeah. Yes.
Are the tiny ALU, is the tiny ALU suspension design still supposed to be locked? Because when I try to go to that link, it says page not available.
Okay. I moved things around, so let me do one thing. I will try to go through that in the class today.
Yeah,
So
maybe it's-
let's see. I think I put that. So I have populated the module sections where we have the lecture notes. So lecture 2 is there. In terms of assignments, I put the week 1 assignment here, tiny ALU.
Yeah,
Click on that, it takes you here.
yeah, and then that link right there for me, it says.
Is not working.
Yeah,
So let me
it's
check
not
that.
available.
It may be issue with others as well. So we,
Look at it.
thanks for pointing it. Yeah, now it's working here.
Anyone else?
Yeah, these are the correct files which I populated today.
Anyone else see if we can access it?
I don't know, it didn't create the link. Let me see if I can create the link. So that will be easier for everyone just to click it. So let's see.
Yeah, I still got, this page has been disabled for this course.
I see.
There's an error.
That's for you also. Okay. Maybe it's visible to me. I may have to enable it for others to
Yeah.
view it. So let's do that. By the way. How do we make it visible?
You are looking at, see on the left when you're looking at where it says files, there's the.
Yeah, because like it has other files also, which I don't want everyone to see. It's a hodgepodge, otherwise it will confuse everyone. So let me see if I can move it in this area. Does it allow to create folder? No.
Oh, I do, I really do actually. Yeah.
Pages.
What's happening? It's just like a vacation, good to like, high school up there. So.
Okay, so maybe I can move it here then. Into lectures. Okay, we still have 5 minutes, so I'll spend a little bit of time. Just move it to a different direction.
And yeah, which is crazy, it seems like they. Small. That's just. But.
We've done this
Exactly.
gone on for a bit.
Okay, can you try it one more time? Anybody can try? Go to the modules and it should show up there, like as you can see here on the screen.
Yeah, let's see.
No, same.
You can't see it either.
We can see
can
the
see the-
sign,
But
but the link for problem 2,
Throws the same error.
yeah, it
You know,
says,
like go to this module section as I'm
Yeah.
showing,
Yeah,
and under that you're saying you're not able to see.
yeah, we are able to.
it's the same issue though.
Oh, okay, same issue. Okay, got it.
Yeah, it's that link to the .sv files for the tiny ALU
Okay,
broken.
so let me create a new module maybe. Week 1. Let's try this now. People on the bridge will get started in a moment. I'm trying to take care of some logistics.
So try to zip it and upload it.
Yeah. All right, let's try third time. Does this work? Oops. Does the zip file work for you? Still?
Oh, wait,
Oh,
let me
okay.
see
I
the
don't make.
module.
How about now?
Okay, now. Zip file we're supposed to be looking at? Let's see. Yes, it looks like now there's a zip file where we can get design, run, and test bench.
Okay, thank you. All right, printing it. Otherwise, it would have been a problem for me. Julia, you joined?
Yeah, I I couldn't find the recordings in the previous.
Yeah. So okay. So the first, what happened is last time or the first time, and Professor Roy helped me start the recording, and that file just disappeared. So I'm going to search on this computer. It was definitely not on the Zoom server. So I'll search for it. If it is still not there, I'm going to record myself and then post it. Like I'll just do a monologue and just post that way. Sorry for that. Like hopefully today I double checked recording is on. So hopefully moving onwards, we should have all the recordings. Okay. All right. So welcome everyone. This is the class 2, week 1. We'll get started. So few logistics, I have uploaded the material on the website. I think I should go into the student view so that I can see what you guys see. So for a week 1 assignment, I have created this tiny ALU and we'll go through that in the class today. So that's the assignment due Saturday. It's an individual assignment and people are supposed to, just set up their environment and run a very simple example. I have also put the Zoom links for all the meetings. So they are already populated. Every week we will have Zoom calls. I'll be streaming as well as recording. For the lecture 1, there was some technical problem because of which I'm not able to publish the first lecture yet. So I'm trying to find where the recording disappeared. So if I can't find it, I will re-record myself and post it to cover for that. So those were few logistics, and in terms of modules, I'm going to use the same PDF and share it. So let's see if that works. So that works. Okay. So we'll use this for presentation today. So the title for this lecture is simulation-based verification. This okay. All right. Let me do one more thing. I will try to join Zoom from my own laptop and see if I can share my slides. Never mind. So we'll go with this. So some announcements, like I have also set up a page for attendance. So please make sure, like, because the class is split between in-class and streaming, track everyone. I think I will pass a page in the class to get the attendance. Attendance has points in the class. So I'll pass this page around. If you don't see your name, just add it to the list. This is from last week. And people on the Zoom, please put your name in the chat if you're there. And in order to make sure, like, this is an active class, just to be fair to everyone, all the students who are in the class, taking their time out and attending it in person, I appreciate that. And people from the Zoom, we want them to be actively attending the class as well. So to make sure everybody is fair to each other, I'll be throwing in some random calls during the meeting, and that will be my way to see if somebody is attending or not. So if you fail to respond on the Zoom, I might, make it an unexcused violation, right? So please be active. There'll be a couple of chances to show up. Just for example, I asked right now for people to put their names in the chat window. So people who will put their names, they will be given credit for class today. And people who don't, they will be late or others. Second thing is, like, I know, like, everybody, a lot of people are working professionals, it takes time to get back, so please put extra 10-15 minutes to get started for the class. It applies to me as well. I work full time, so I'm putting 10-15 minutes extra to get here. So I will appreciate if all of you also do the same. So late will be not excusable in terms of attendance. Secondly, last time I think I did not provide structure for the class, like what chapters we'll be covering. So we have 2 books assigned. So I have kind of distributed them evenly throughout the weeks. And there is a possibility we may be ahead or behind based on how fast we go. So I'll be adjusting those during the weeks, but this is a rough outline. There's a lot of material to cover, but we'll make the class so that it becomes digestible and you can follow along and But I will recommend that you read the books as well, because verification is such a vast field. There are a few things I will make you focused in the class so that you get out of the class feeling that, hey, I learned something and I can use it practically in my job or apply for a job. But at the same time, verification is a very fast field. So I will recommend you to read all the chapters as well. So a lot of quizzes and homeworks and midterms will be based on these. I use the word quizzes. I'm thinking about it. They will be graded, but just to make sure you are reading chapters, we'll throw in some quizzes. We may throw in some quizzes as well based on the workload you guys will have. I am sensitive to workload, so don't worry, like we won't make it too heavy class for anyone. If you start to see that I'm throwing too much work at you, let me know as a feedback. I do adjust it during the session, right? So those are quick administrative updates. Any questions before we jump into the class material today? Anybody on the bridge has any comments? To start checking this as well, so I can keep a track on chats here. So just to share here, like I just wanted to let the class people also know who all are there. You can see the names, right? All right. And I hope, as we spoke in the last class, you are working on forming your teams. So please be prepared next week to give me the names of your teams you're working with, right? All right, so let's jump into the material. Last class, we talked about the product development cycle in a real world, how it happens. And we broke that product development into stages, right? The first stage, we called it as the requirements gathering, where you're understanding the customer needs for making a product. And then you take those requirements and needs and form it into requirements documents. Like, these could be specifications, in terms of what does customer want in terms of features, right? Like on a cell phone, we want a swipe left, swipe right. We want cameras of such resolution, blah, 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 right? So those are the product requirements which you capture for a product. And then based on those requirements, you define the architecture, how the system will work. And based on the system, you will break it down into components, ASICs, FPGAs, how all of them will fit together as an architecture for that particular system. And that will translate into ASIC engineers or VLSI engineers to go and make those individual components, which we call as chips or ASICs or FPGAs, you name it, right? Like there are different ways to create those. So all of them are based on this product definition stage, which feeds into front-end design, which we discussed last time, where you have high-level design, then you go into logic design, and then you do physical design. So you hierarchically approach this architecture and design a chip. And then once you're ready to tape out or send it for manufacturing, that will be sent to manufacturing the chip. And once the chip comes back, we validate the chip to make sure it is functioning as we specified originally, right? And then once the validation is finished, we sell the parts, right? We launch the parts and sell it. So the stages before the manufacturing we call as pre-silicon verification, and validation is the post-silicon validation. A lot of times engineers use it interchangeably, not a flaw, but just as a guidance, we use verification and validation words as we discussed last time. Now we jump into schedules, how it aligns with the schedules for a product. So if you put it a timeline on this whole operation we discussed, architecture starts first, and it continues and overlaps with something called microarchitecture, where microarchitecture is breaking that architecture into smaller pieces. And it's a divide and conquer strategy where you figure out what will be done when. And based on the microarchitecture, you will design your product, then do the RTL coding. As you can see, there is a start point but the endpoint overlaps in all these functions, right? So as you can imagine that when a project starts, the team size keeps growing bigger and bigger as more functions come on board, and some of them will taper off, go off the chip, others will continue. And verification is one area which we talked last time, spans the most throughout the duration development cycle, and then you tape out, right? So this is just a recap from last lecture. This is not going that well. All right. So now we want to narrow down into pre-silicon verification. What are the common techniques? There are 3 techniques. One is there a comment?
Slides is not able. We are not able to see slides, Professor.
Oh, you're not able to see the slides? Okay. Let me figure out what's going on. So am I not sharing? How about now?
Yes, Professor. We are.
Thanks. We can see the slides.
All right. All right. So there'll be a few slides missing from the recording as well. Hopefully from this point onward, it should be okay. If you see any issues, let me know. We'll adjust it. Just to rewind, pre-silicon verification has these 3 main techniques. There are several techniques out there, but majorly we are focusing on 3 in PCC, I think based on the classes they teach and all. So the first one is verification environment and methodology, where we work with RTL. Here, there's a big emphasis on methodology as well as techniques of doing the verification. That's the class we are doing today. Other methods are formal verification techniques. They are becoming very, very popular because we talked about the design complexity last lecture, how the designs are becoming more and more complex with the Moore's law. So formal verification techniques are becoming very important in future, as well as the third leg of this tool is hardware emulation. So we use emulators where you can emulate the design before tape out, where you can run bigger workloads with software to test before you send your chip to the production. Right? So these are the techniques, and here we'll be focusing on the verification. So in this diagram, like it's hard to see, which will expand more. Ultimately, you have a design which is going to tape out, and you need a way or methodology to test the design. And for this, testing that, we have been over the several decades, the methodologies have evolved to allow you to have a verification environment in which you can build your verification components. And then you will be sending the stimulus, you generate a stimulus and test your design, which can test your design. And then you need coverage, which ensures that the tests are doing enough testing, which gives you confidence that your chip is good enough and it's bug-free, right? And then finally, you also have checkers and things. Checkers are basically testing whether your design is doing the right thing or wrong thing, right? So you will see the terms of constraints, checkers, coverage, collaboration used quite often in this class. I will be going over this topic over and over again, like, we'll go in depth sometimes and then come out and use those terms. So for verification terms, as we go in this class, I may throw some terms which may be new for people, but at some point we'll be covering those terms in the class, right? Like, so that's the focus, like all the concepts, they get covered. And that's why we have 2 books. One of them is focusing on UVM as a methodology, which you can take as a skill, and you can immediately apply it to your job. And the other book covers more broadly so that you understand what is verification, what are the nuances of those verifications, right? So both books work together to make you a good verification engineer at the end of the day. All right, so this is straight out of the book. So verification is a verification cycle, right? Like last lecture also we talked about verification cycle, that during the pre-silicon design, we over and over go through verifying the design, right? Like, so we talked about hierarchically how we make FUBs, clusters, bigger units, and then SoC. And at each stage of those design development cycle stages, we verify that piece. And then we find bugs, we go back and fix the design and re-verify, right? So this becomes like a iterative cycle through the pre-silicon development stage. So in this, quickly going through few terminologies here. So we start with the functional specification, like where architects or designers will write functional specification for a particular design block or cluster or SoC. And then based on that, as a verification engineer, you will be required to first develop a plan that, hey, here is what we want, what we are doing to do as features. How are you going to verify it? And how are you going to ensure that we are ready to ship our product? And that's what this verification plan covers. And then once the verification plan is there, then we go into development of our verification environment. So based on the planning, we'll figure out what kind of environment we want to have. So based on what are you testing, right? Like, are you testing a FUB, which is a small design block, or you are testing a cluster, which is bigger than that, or you're testing a SoC, the entire SoC. You will decide what kind of verification environment I want to use for this project, and then propose that and architect that verification environment. In this verification environment, you will be, developing your test benches, your components, checkers, all the C's we talked about. And then you will start running your test. And then when you run your tests and regressions, you'll be finding issues. You have to find where the issues are, so that there are debug techniques which are used in pre-silicon. And then based on the debug, you'll find root cause where the bug is. You'll give that feedback to the designer that, hey, we found the bug. This is why your test is failing. Designer will go and fix their design and give you new design back so that you can retest it, right? And then you keep doing it over and over, and then finally you go to fabrication. And then, there'll be always be some bugs found at later stages in the design development cycle. So you keep analyzing that, hey, why my bugs are escaping? You take that feedback, bring it back to your environment and fix your environment and so on, right? So this becomes like an iterative cycle, which you go through 2-3 times, in real world. Like, for example, Intel has our own methodologies, AMD will have their own, NVIDIA will have their own. So every ASIC as well as FPGA company, they define their milestones for product development, and they go through these iterative cycles. Pretty much it's similar in terms of iterations, but milestones may be different across different companies. So it's good to have that bigger view, bird eye view of how this whole thing is working. Now let's look at the first verification planning. So in terms of verification planning, as I mentioned earlier, last class we talked about where the verification engineers are spending most of their time. And this study was done based on 2020 results from surveys they had conducted in the industry. So a small sliver of the efforts of a verification engineer goes into verification planning. But this small sliver has one of the biggest impacts for how good of a life of a verification engineer will be during the execution of the project. As well as this small sliver also dictates almost the health of your product, like how healthy your product will be. So it's a very important field, which often gets ignored, and it's a bit ambiguous. So as you gain experience as a verification engineer, a lot of experienced people work in this area in any company. So it's good to know about this area and build those expertise as you become a validation expert in your career, right? So what does verification plan include, right? Verification plan includes, you will be specifying tests and methods, how to verify a feature, what kind of test I should be developing so I can make sure that the functionality of the test is correct, right? So how you do it. Like you first start identifying what the features are to be tested. And based on that, you will architect a verification environment, or like, how I'm going to send the stimulus and how that stimulus will make sure that functionality is being tested, right? As part of the verification plan, you also think about tools. What kind of tools will I be using? Which kind of simulator I'll be using? There are multiple companies out there who provide simulators and their capabilities are different. A lot of these companies do provide verification IPs. So standard simulation-based tools are most common, and you will be deciding those based on your previous projects, or you might have new needs. Based on that, you'll be deciding those things. You'll be deciding on what kind of debuggers I need to bring in as tools, what kind of coding languages we'll be using, like, system Verilog and Verilog are common, but you will be deciding that, hey, do I want to bring in UVM into my verification methodology? Do I want to bring C-based test benches? Do I want to bring in system C-based test benches? So a lot of decisions are being made as part of this verification planning. And these tools make the life of a verification engineer easier or hard. Like, for example, if you bring in very nice debuggers, later on, you'll find like, 40% of time is spent in debugging. It can make life of your verification engineer very good. But on the contrary, if you have very primitive debugging tools, they will be burning midnight oil to figure out where the bug is, right? Like some bugs are very, very hard to find. So just to give it that flavor of why these things are important, right? And then as one of the things is, at the end of the day, we have to tape out a chip or, send a design for production. How are you going to decide, right? Like last lecture, we talked about, if you look at all the logical states of a design nowadays, it's astronomically big number. You can't verify everything. So a verification planner has to decide ahead of time, what is my criteria to call verification done, right? Like, so they have to decide upfront, and that also is a very important decision, because that can make or break company's balance sheet. As we talked last time, that, hey, if you send a buggy chip, customers will send you back and you have to pay them, royalties or like, damages. So this can be very expensive for the decisions, right? So as part of that, like, they make sure the functions we decided in the beginning, they are at least covered. And they also have to think very carefully that what functions we are not testing, right? Like not everything you can test pre-silicon. Like, for example, there are a lot of software dependencies which you may or may not be able to test in pre-silicon. So you have to really identify carefully what functions you won't be testing in your verification environment, right? And that environment, like, we talked about FUB or, cluster or SOC. At every stage, a verification architect will be deciding that, hey, at my unit level test, I cannot cover X, Y, Z, right? So those functions they can identify, so that the person next in the SOC, he can say that, hey, this was the gap in the ULT testing. I need to pay special attention to these areas. And similarly, the SOC architect can say that, hey, I cannot test these functions in the SOC. So post-silicon needs to make sure those features get tested, right? So they can pass the buck, but carefully, right? Like there's a huge cost associated with passing that buck, because as we talked last time, sooner you test something, sooner you find bugs, less expensive is for your product development cost, right? And finally, estimating the resources, people, hardware, software, schedules, cost, all of these things also, these are a lot of time non-technical functions, but a verification planner does get involved into those discussions with project planners or program managers who will be tracking these items. But verification planner will give these inputs as a key contributor for that decision as well. Moving on, next piece on that cycle was environment. So verification environment is extremely important as well. So this starts to bring us in some of the discussions around methodology, right? One of the typical system Verilog test bench environment looks something like this, right? Like at a very high level view, on the left-hand side, you have a design under test or design under verification, and you build a test bench around it. And the test bench, what it is doing is it's sending some stimulus to your DUT and getting the responses back. And you're just your test bench is just checking whether your responses are as expected or not, right? If the responses are as expected, that means your design is behaving correctly. If there is something wrong, there's something wrong. So this is a very simple test bench environment which we have been following for multiple decades again, right? But what has evolved is how to bring more efficiency into this environment. So one of the system Verilog based model we have is something like this, where you have the design under test or verification or validation, and you build modular components or verification components around it, right? So to test your design, you need stimulus components, like something which can generate the stimulus, that's where your test writing is. You write some tests which generates your stimulus, which can be applied to your design, right? And that stimulus is driven by a driver to your DUV or DUT, right? Similarly, like there is an environment model which puts all of these test benches together. And that is also driving all of these pieces together, like, how your design will be initialized, how your reset will happen. So those kind of things, how does the entire environment looks like, that becomes a modular component and gets applied to your DUT as well. Then other pieces which are more passive pieces, which are receiving they don't drive the design, but they receive vectors from the design. Like there are monitors. What monitors are doing is they are protocol monitors. Like you might have AMBA based designs, you might have PCI based design. There are some standard protocols. So they could be testing those protocols that, hey, is the design responding correctly to those protocols? Or they could be custom protocols as well in a design, right? Like, so you write monitors whose job is just to observe what's happening in the design interfaces. And it just keeps log of all those events which are happening at a design interface. Based on those monitors, then checkers come in, like, checkers are checking whether those responses are correct or not, right? So you write checkers as components. And then finally, scoreboard is tallying those together that, hey, as part of my coverage or, as part of my goal of this test, I want to keep it a score of what stimulus went, what were the responses, and am I collecting everything as expected or not, right? So one of the things which is fundamental to all of this is coverage monitoring. As we talked about, what coverage monitoring is that as you are running the stimulus, you want to see how much design is being tested. So that's what coverage is doing, like where you look at your entire design and you figure out, based on my tests, how much design has been validated, right? And that's a very big area. Again, going back to the original problem we talked about, that our design space, logic space is so huge, we have to know how much we have tested, right? So that's what coverage does. And this is a big field, like we'll spend more time on it in subsequent classes as well. So that's a very big component, which is like underlying. So one of the evolution which has recently happened, or which has been happening, is we have started to make our verification coverage based. That, hey, you start with that. If your end goal is to have 100% coverage of your design, that, hey, I've covered entire design and with my verification, why don't we start as end goal as a starting point? That, hey, my goal is to get 100% coverage. So let's build all of these components based on coverage. That, hey, each of these components should contribute towards completing my coverage, right? So that's one of the methodology evolution, which you will see in a practical world, where we are starting to build verification environment based on coverage as well, right? Now going deeper into environment components. So one of the things is they have to go for completeness. We have talked about it before. So, for example, in a design, you can say that, hey, my design is doing some functions, right? But when you look at the protocols, there can be variations in the protocols, and you have to make sure that all corner cases are being covered. So completeness is one of the key objectives that, hey, you want to, in your verification space, take care of all the corner cases, take care of all the possible variations you might have in your protocols, and make sure your components cover all of that to make sure it is complete. And it's able to drive all possible behaviors as well, right? Like a design may behave differently or can be configured differently. So all those behaviors should be tested as well. That on my phone I have night mode, I have day mode, or I can reduce my brightness. So all of those possible configurations of your device or device in a test has to be ensured that you have covered all of the variations as well, or configurations as well, right? And max stress means, like, we talked about corner cases. That last class also we talked about one bug which happens in 10 raised to power 20 cycles of computation. So how do you make sure that those corner case stress conditions have been tested as well, right? Like, which are really, really hard to reach verification space. Second environment behavior is configurability, that your design or verification environment should be highly configurable. That because we talked about modular development, like, we try to build everything modular, starting from a small design, which is FUB, to SOC. And as you build the verification components for each of these stages, you want to be able to reuse all of them. And one of the ways to reuse it, configurability of those components. So verification components going into the environment has to be highly configurable. And so that's a very good feature for verification environment you're building, right? And that's part of the architectural decision, that, hey, how I'm going to take this entire chip and break it into pieces where which is so that I can distribute across large team. We talked about, hey, a design team could have, or a development team could have hundreds of engineers. How do you utilize them effectively? One of the ways is to break your all these components into pieces so that parallel development can be done. And you have to make these components talk a common language so that people can, or these components can have reduced dependency on each other. And this is the reason we built our larger teams in the project for the class, so that you get that experience of how to communicate with other larger teams, how to how to decide how to distribute your work between different engineers and so on, right? And final piece of this environment components is the debug hooks. We talked about debugging is very hard. So the way it is achieved is you provide the debug hooks in your designs and verification components, so that if something fails, you can quickly reach what failed. Like, one example is you have seen we put printf statements or display statements in our code. Based on the type of error you are seeing, you can quickly see that, hey, in this design, line number 30 has a display error, right? So those kind of debug hooks, and debug hooks are becoming more fancy, where there is an evolution there as well in terms of development. And as we talked about reuse and configurability, you want to build the debug hooks where it can be useful for a designer, it can be useful for a verification person, and it can be even useful for a post-silicon validation person as well, right? So basically, we will try to model a real world scenario in our class as well, where we work through these similar situations. So you get that flavor of what are we talking about in terms of specification and communication also between team members, right? Next piece of our verification cycle was we talked about was stimulus. Now coming down to, now that I have my test plan, I have my environment, how I'm going to generate my test stimulus, right? Like ultimately, this is the crux of all of the things we talked so far. Ultimately, you want to test a feature and that feature should pass or fail for a design. So the way it is done is you have test generators. So test generators are generating some sort of behavior or like, sequence of operations or something which can stimulate your design to start executing a sequence of logic, right? So your test is going to, you will generate a test and then you will use some sort of driver to drive your design under validation, right? Ultimately, your DUT or DUV has a pin interface. It could be data pins, operation pins, reset clock, all those are visible outside your design. And that's what you drive into your DUV. And what you're doing is you're generating tests and sending those through driver to your DUV, right? So initiators who are initiating these stimulus, there are several subcomponents in it, like drivers, behavioral models, like you might be writing behavioral models, agitators, irritators, injectors, generators. These are some terminologies used, and these are defined in the books also. Each of one of them purpose is to generate tests and improve on them, reuse some of the tests. For example, a irritator takes existing stimulus and changes few things, irritates the stimulus which is going in, and it can generate very nice corner cases for your DUT, right? Injectors can force certain pins at certain times, and you can generate interesting verification scenarios for your design, and so on. So that's one piece. Evolution here is instead of your test generator to directly talk to the pins, you can see we have put some drivers which are driving it. So once we have separated the pin level wiggling, can there be a situation where you can use standard protocols instead of very design specific interfaces? So that's a important function which you can introduce in your design as well as in your test environment, where you can move towards standard interfaces, right? And that's where, like, you'll see in subsequent classes, UVM plays a big role, where they have tried to define these interfaces between design teams and verification teams. So what we are trying to do is at the DUT level, there'll be like low level, bit level stimulus to be driven. But at a higher level, you can abstract that and work with protocols and other abstraction levels, which we'll discuss in subsequent classes. So this is on the initiator side, and similarly on the responder side, that you are generating something, but for example, when you're working with let's say you're working with ALU, which we will be using tiny ALU. So tiny ALU, who generates the operations for your ALU? Where do those operations sit? So there are a lot of logic missing in just the tiny ALU, right? So in order to mimic the behavior, sometimes we introduce these components called responders. Like, if design sends a response and there is no other component to respond to it, we can sometimes generate the responders, right? Like, for example, your ALU suddenly makes a memory read request or mload or load request or store request. You have to have some sort of responder. Even though design does not exist for that memory, you should be able to respond to it. And these responders, you don't have to develop a full memory controller for your load and fetch instructions. You can just have a responder which just responds that, hey, I received your request, I'm just acknowledging it. I'm not behaving like memory, but I'm going to just respond to it. So these responders and initiators, those make our stimulus working and for various abstraction levels of this DUV. So all these components, like you can think about, we have test generators, like, we have arithmetic operation generators. So when we talk about these test generators, we can write them in various buckets as well. Like, you could have a test generator, which is just generating arithmetic operations. All it does is, hey, add, multiply, these kind of operations it does. Then you could have more complex, like, this is a fmul is a CPU primitive. You could be generating sequences for just those fmuls, right? And then you could be generating sequences for logic only, right? So you can separate them out, and then based on your test stimuli, then you can select which of these operations I want to send to my DUT for driving, right? And then you have some sort of responder or some sort of driver, some component before the driver, which will additionally irritate those stimulus we talked about, right? Like, so your test generators are generating some stimulus. Irritator is just changing few things in that to create corner cases, right? And then you could have some responder that, hey, I don't have cache in my design, so I'm going to put some dummy cache or responder, which will respond to my cache requests. So this becomes my test bench, components, which we talked so far, and then they can interact with the driver to send pin level signals to the design under validation. The advantage of this kind of separation is that you can almost imagine that I can put one engineer on each of these tasks. And if I define this standard methodology or standard interfaces or protocols, then they can work independently. I can just give them a spec for the protocol, and that engineer can work very independently. If I don't have that, then then they have to talk to each other, have 10 meetings to discuss that, hey, what's the behavior of this pin, that pin, right? Like, to avoid that, you create these separations, and we are moving towards a methodology-based approach for verification. All right, so now we talk about the other pieces, monitors. So monitors are self-contained observers. So as we talked earlier, monitors just are watchers, right? Like, so they are just watching what's coming out of DUV or what's going into the DUV. So they are like probing what's happening, right? These observers can be used to verify correctness of the functionality. The results, are the results correct? When I did A plus B is equal to C, is 2 plus 2 really 4, or is it 5, right? They can also be used for protocol adherence, right? Like, so protocols, I don't know, you might have done some, have you guys done any protocols in other design classes like AMBA, or do people have experience in that? I'm sorry, speak up. Okay. On the bridge, like, do people have experience with protocols, standard bus protocols?
Yeah, we've done communication protocols, but nothing very high level. Nothing even, I don't think anything super sequenced either. Just,
so one of the characteristics of protocols is they get published as the architecture spec to all the engineers, whether they're designers, verification, or anybody else. And they define specific sequences, like, for example, for memory interfaces, they will say that, hey, this is how you send the addresses on a bus. And so much clocks later, memory is supposed to respond with the data. Like, let's say you're doing a read op on a memory, protocol will say that, hey, this is how you send the address, and this is how much time you should keep the addresses on the bus, and this is how you send the enable bits, and memory as a component can respond after X number of clocks in this format. So protocol will actually define that. And one of the things is protocol specifications are usually 100 pages long or something, like really big. And as a verification engineer, your job will be to make sure all the components sitting on that memory bus adhere to those protocols, right? So you will be writing those protocol observers to make sure all the protocol requirements are met, right? So this is what it means by building observers for your design and verification environment. And these monitors can also be used for debugging information that, hey, like as you are checking that after these many cycles, address is supposed to disappear and, you know, data should come. If it didn't happen, a monitor can flag that, hey, I saw an error and I saw this error on 1,020,000 cycle, right? Like, so that can help debuggers to figure out what happened, why it failed, where it failed. It won't say why it failed, but it'll say where it failed, right? So important information can be used. And this information can also be used for coverage or scoreboards, that these monitors can be used for providing those things, because when you're observing, you can say that, hey, I saw this opcode pass through. So those are done, right? So they can tell to the coverage monitor that, hey, on my bus, I saw these transactions and you can mark them done, right? And so that information can be used by coverage. Or scoreboards can say like, hey, my test was supposed to check for that address bits 13 and 14 must toggle. Did you see that? They can, you know, these scoreboards can go and ask monitors that, hey, did you see address bits number 13, 14 toggling? If yes, then my coverage is done on those, right? So those are some of the use cases for these monitors. And checkers, they take it next step where they're actually checking along with just monitoring, right? So the functional checkers can be implemented where you can define, you know, a temporal or, you know, different kind of checks can be done that, hey, after 10 clocks, XYZ must flip its bit, right? So you can write those kind of functional checkers and they can be pretty useful as well. And these come really handy in hard to, basically the completeness concerns also, right? Like we have been harping on this topic about verification has to complete. So all this information can be used to make sure that we have completed our verification. Now, for checking, there are different strategies which can be used, right? Like, so when you're checking information, in the last class, we talked about white box, black box verification. So checking can be done just at the interfaces, that you can just look at the one of the component or that in this case and say that, hey, I'm going to see, just monitor the inputs and outputs. And I will just make sure the inputs, the stimulus is coming correctly and the output is corresponding to this input. And I just look at those and tell whether design is behaving correctly or not. In addition to that, you can put some design context around it, like where, you know, we talk about memory, that if there is I have some missing data, I have a miss for a operation in my CPU, then I'm going to go out and get some data from cache, right? So, so those miss as an operation is very design contextual. So you have to go out and go to a cache, and there may be a responder or actual cache here, which can be connected to this, right? Further, it can be more architectural based, like your checks can be done where you can take multiple IPs inside your design into your checking strategy, that in addition to input output pins, I'm going to also check for certain behaviors inside the design, right? And finally, it can be architecture based, where in addition to these things, I'm going to also account for entire SoC architecture, like feature wise, like end to end is my feature being checked, right? So different checking strategies can be used. And this again goes back to the hierarchical approach and abstraction levels, which we can drive into our checkers. And finally, we have the scoreboard. So so far, like we talked about all the components, and the scoreboard is just a nice scoreboard, which is keeping the score of all the operations, all the things which are happening in your verification and design, right? So this job is just keeping track of everything which is going around in the verification environment, right? So this is a temporary holding location for the information. Scoreboard captures the transactions, and it checkers may do the query inside the scoreboard because it's keeping track of everything. And so it is capturing the data from the design interfaces, but not really provided by the initiator, right? So one of the characteristics of scoreboard is it is keeping track of important information, not like everything. And as you will see the methodology evolution, like there are reasons why we don't include certain non-relevant information inside the scoreboards. Can someone think of one of the reasons why we won't keep the information about initiator in the scoreboard? Let's say in your test bench, you have initiator, you have a DUT, you have a responder. And this statement says that, hey, I'm going to just capture the design information, not really the initiator or responder. Why do you think that will happen? Think in terms of the component. Scoreboard is a component, and you're building it as a component for a reason. Why are you building it as a component? Anybody on the bridge? Yeah, go ahead.
Because you might have initiators that are supposed to make the design fail to test corner cases or failure rates, and you wouldn't want that displayed in the scoreboard, maybe.
Yeah, that can be a reason. But the main reason is, with the hint I gave you, reusability, right? Because you want to use this scoreboard at multiple places. And in some environment, you may not have that initiator. You may like to remove that initiator and put actual design there, right? You talked about the irritator or initiator may not be needed in certain situations. Then why are you keeping score of that, right? So reusability as well as desired need, what you need in the scoreboard is also a good reason. All right. Another thing is scoreboards are also used for creating reference models for your design. Yeah, go ahead.
So
There's a comment.
in scoreboard, there is no initiators. Then how can we do that where we did mistake in which test?
Sorry.
If in scoreboard,
Mm-hmm.
there is no test generated,
Mm-hmm.
there is no initiator, then how we can understand that in which test we did the mistake? In which
Yeah.
test there is no.
Good question. So basically, you have to look at the entire environment as a whole, right? Like scoreboard is keeping track of certain things, but there are monitors. We talked about monitors. We talked about initiators. So as you develop other components, they could flag the error. That, hey, because this is the job of monitor. That monitor is supposed to be monitoring. And if you saw something wrong, I can put a checker there. Checker as a component which checks for certain things, and they will flag the errors, right? All right. So these are like going back to I think I should have put another slide, but just to wrap things up here, we talked about all these. This slide. We talked about various components of the test bench environment and what role they play, right? So we are covering the basics of the verification, and these concepts, whether you are using System Verilog or whether you are using System C, or even if you are using UVM or OVM, all of these methodologies are evolving together for similar kind of components. So using the simple method, we just wanted to explain these components, and you will see more use of it as we go in deeper into the unit. All right. Now let's talk about the stimulus and verification techniques. Last class we touched on black box and white box testing, and we'll introduce something called gray box testing as well. And as the name is pretty obvious, what we're saying is it's somewhere in between, right? Like you have black box testing where we have no idea what's there inside the design. We are just looking at the interfaces, and what we talked last time is in order to know, without knowing what's there in the design, you will just permutate through all possible combinations on these inputs and outputs and see what happens, what's the behavior, and just take note of that. White box testing, on the other hand side, is done usually by the designers, because designers know their design, so they can write some tests to know how to test my design, right? Or they can work with a verification engineer, which we will be emulating in our project, where your designer will tell you how the design is, and as a verification person, you write tests knowing about the design, right? Advantage of this is like now suddenly from this humongous state space, now you can really narrow down to few functional tests, which can test your functionality of your design, right? So that's the advantage of white box. And gray box is somewhere in between, where you take some design knowledge and some work on the interfaces to come up with a verification strategy where you can accomplish completion of the design verification. So black box has what are the advantages? It's resistant to any internal structures or timing changes. It won't care about what's happening inside the design. It will be independent of reference model. You don't need to know what the reference model is. You can just work with the stimulus. Disadvantages is like, your observation is not there, right? Like where if something fails, how do you know what caused the failure? How do you know like what was design supposed to do, whether it's a legal failure? Like for example, there could be states where it's illegal state. Design doesn't even intend to do that, right? Like, and you're trying to create that corner case. So those kind of things are not good in a black box verification. And it's harder to check ambiguous cases. White box, on the other hand side, is like, they are good on debugging. Like, you know the design, what's supposed to happen. I can quickly find out what went wrong and debug it, right? Whereas think about like black box, you are just throwing vector after vector and trying to figure out based on the output what the behavior is, what it is supposed to do, right? We covered a case of mux, just observing output or a gate, like for example, AND gate or NAND gate. Just observing the output, you can figure out what the behavior is supposed to be. Whereas in white box, you actually get that information, and then you can reduce your work in terms of how many vectors you have to generate. Disadvantages is a high maintenance, like you have to understand the design. Like for example, verification engineer, like as a verification engineer, your job is to verify. Like, so you will build expertise in test development, test bench development. But if you have to do white box testing, you have to know the design. You have to understand the design. Then only you can test it, right? So it increases the work quite a bit and such, right? And so balance of the two is gray box is something which is typically used, and that's what we'll be testing, using it in our projects as well. That hey, you have some design knowledge, and and you can work with that to do the verification. Now, verification. The book also talks about testing strategies and test benches. So there are deterministic test benches, where early verification cycles will tell you basic functionality to be working, right? Like where you have very deterministic test that I'm supposed to test for A plus B is equal to C. So I'm going to send A, I'm going to send B and check for C, right? Like, so it's a very deterministic way of telling. And I can even be that deterministic where I can say that what values should I put on A and B so that I can test it for C, right? Like for example, if you have a 8-bit adder, so you have 8-bit input A, B, and C. So I can quickly put, FF because output is supposed to be higher than 8 bits. That's what will be behavior of your design, right? Like, so it's a very deterministic knowledge about the test, which you can write, and your test benches are built for that deterministic behavior. Again, like as you can imagine, it requires you to know the specifications and implement those using multiple tests and sequences to test your part. Second is you want to build like self-checking test benches. So we talked, I think we understood the importance of checking while you're monitoring your behavior of stimulus and all. Your test bench should be self-checking where, like, if something fails, it flags by itself that, hey, here is a failure, please take a look, right? So all the tedious checks can be done by your checkers, right? Like, so your test bench should be self-checking. And there it has concept of golden vectors, reference models, and transaction-based reference models, right? So what does these terms mean in the book, right? Like, so golden vectors are that before you even run the test, you know from somewhere that what's the right behavior is supposed to be and what are the correct vectors which are supposed to come for which your scoreboard or checkers are supposed to test for, right? So what is typically done is, like, there are multiple ways of modeling your design. Like, for example, you can write a C code, an architect can write a C code for your behavior of your design. And using that C code, you can generate something called golden vectors that, hey, my architect wants this behavior out of this design. So using that C code, you can generate your golden vectors and store them somewhere. And then when you run your RTL, you can go and see that, hey, did my RTL produce same output as was expected out of golden vectors? Yes or no, right? So that's a very common methodology which is used in the verification world. Then you can have reference models, right? Like we talked about the C model which you have created. So instead of generating outputs and checking them, you can just use the model itself in your test bench to see if that behavior is mimicked or not. And you will see example of this in this tiny ALU. Like, you will see we have a scoreboard there and that uses a reference model. And finally, like, in TLM world, you can create like transaction-based reference models. We talked about bus protocols, and this is pretty common in bus protocols where you can put the transaction-based reference models also, and which increases the abstract level for these things. Out of all these testing strategies, whatever we deploy in terms of how we are generating the test, deterministic or not, how we are checking them, one of the underlying requirement is that the checking has to be complete, right? Like, and second thing is complexity of maintaining these test benches and testing strategies. Like, as you can imagine that, again, going from FUB to cluster to SOC, a lot of components will be built, a lot of checkers will be built. How do you maintain them, right? Like all of them to work cohesively with each other? Sometimes cost of that itself blows up on you, right? And same thing, we have talked about reusability multiple times in the class so far. So that's important as well. So let's summarize it here, right? Like we talked about, so that kind of concludes our test bench structures. We talked about the DUT, we talked about stimulus generation, drivers, environment, coverage, checkers, monitors. So we talked about all these components, and there are these basic 3 C's of validation: constraint, checker, and coverage. So these are the 3 amigos for test bench structure, which you have to always keep in mind, right? Constraints, the stimulus has to be random constraint stimulus. How how you're controlling that. These constraints should be able to access a lot of your design quickly. Checkers is the second amigo. Like it's supposed to have, we want to have self-checking tests. We didn't talk about assertions. We'll try to cover assertions in next lecture. But assertions are kind of system Verilog. Assertions are used for creating those corner case checks in your design itself. So just a quick word on it is like, what is being done is like, as verification people write checkers, from methodology point of view, system Verilog allows you to write assertions in your design. And as designers or micro architects are developing their design, they themselves can code it in the design so that verification people can just use those assertions. So we'll talk about that in a little bit more details next class and such. And we talked about the reference models and golden models, which can be used for checking. Coverage, main question for coverage is, are we done yet? Right? Like, are we ready to tape out? And you will see coverage as a pretty dominant amigo because it's becoming very, very important. Like I cannot emphasize on it, but for complex designs, this is one of the big problems in the industry on when do you decide to tape out, right? Like we talked about the cost of bugs later on. So verification engineers are always sweating that, hey, what if one bug slips in the silicon? It's going to be extremely costly, right? So coverage is the methodology which helps you cover that. Coverage-driven test benches and test verification approaches are good. And there's a fourth amigo added to the mix is called collaboration. And you guys touched on it in the first class itself that as the team sizes grow huge, collaboration is very important, right? Like how do you make sense out of this huge hierarchies of design and verification components, and how do you make them work with each other? So collaboration is a fourth C, which is important. Okay. So with that, like I think we'll pause here. I took a lot more than 20 minutes extra. So we'll before we pause, any questions? Are people still there on the bridge? No response means nobody on the bridge.
Yes, Professor. No questions, Professor.
Okay, thank you. All right, so in that case, we'll take a break here. How much time should you guys need? 5 minutes, 10 minutes? 5 minutes is good. So let's meet back at 6:15.
Professor, about the first lecture, some of us were not aware the first lecture was in person and not online, so we couldn't attend that. So can you just brief us about the key points discussed in the first lecture?
Yeah, so for the first lecture, we covered the overview of the verification landscape. So I have posted the slides on the canvas, so you can refer to those. And I will try to arrange a recording also for that material. So we did record last time, but due to some technical difficulties, we couldn't find that recording after the class. So I could not post it. But there is material which you can refer to. And then I will also, in case I can't find the recording, I will re-record it myself and then post it. In terms of what we covered was basics of verification, like, importance, what we need to do. So that's what was covered in the first lecture.
That's really helpful. Thank you so much.
No problem. Yeah.
Can't access the design files for the tiny alien.
Yeah, like I just fixed it. Now can you see it? Like
I just checked it a second ago.
okay, so I need to fix it.
It was just a file.
I moved it under the modules. I think I need to update the assignment and fix the link there as well. I think the link in the assignment is still old.
Thank you.
That's what I'm doing. That's what I'm doing. Oh, hi, what's up? Right there. Not quite. That's not pretty rude. Like I've heard you all of my school.
Yeah, I think I used it for another class. I don't remember.
Yeah.
This is part of this, like, I hate class. And I understand what it's doing. Yeah, just. Why are you responding to Google chat? I don't know, professor, because you know what, Google saw me, or Google chatted me since like 2015. This, I love it. Kind of remarkable. Yeah, I've had it like a year and a half. Highly recommend as like a student investment, but if you're like less than a year, if you're a degree left, you're not invested in it, because I find it's too big for an e-reader unless I'm doing academic reading. I have a smaller cheap, like 6-inch Kindle. Yeah, for like reading pleasure, but as far as like. Yeah. She just I just got this for like 20 bucks on eBay, and I was like, okay, fine. It's great. Also, it was great because I was like, I am absolutely true. Bullshit, sci-fi.
Oh, yeah, I'm done.
beach
Right,
reads, like. I was like, I don't even know if I'm reading a young adult novel, right? So, yeah.
It's a part of the fun.
It's part of
Your cover is displayed that everyone, is that werewolf?
Yeah. Yes, yeah. They will
They
take
never get them back
Forever.
until you take it off their mode.
That's fun. That's
Yeah.
fun. The partner always doesn't quite.
That's the put on grip and then.
Oh, yeah.
The weight you've been waiting on, because available. but you can-
I checked, I did by the way, because I'm to buy.
If the other one. Yeah. But yeah, I really. I don't find it. I'll be interested to see. How that one.
All right, so let's get started again. So what I need to do is. So in our assignments, like, so I have given this file list here, lectures export.zip, and this contains then, and the name of this file is a little bit misleading, but it contains the tiny ALU code. That's what we'll be covering in the class as example for understanding the concepts we just discussed. So we discussed like broad verification concepts, and the purpose of this tiny ALU is to show you how it actually all the pieces fit together into an actual verification test bench. So let's first look at the design. What tiny ALU is doing. It's a very small ALU. It has 2 input ports, A and B, and then you supply it a operation code. And based on the operation code, and then you give it a start pulse, and then you will get some results and a done signal. So inside the design, So starting with the black box method, like, that there is no inside knowledge on how this ALU is working. And if you just throw some stimulus at it, like you will get some outputs here, which are a little bit hard to see, but what you will see is that, you have the clock, A and B, and the operation you supply it, and then you get your output here, right? The result is coming on these 16 pins. And then based on when the done signal is asserted, you can see that for various ops, what this ALU is doing, right? So this is an example of a white box method where you just applied some inputs and you can observe the output and see what's happening, right? Now going to the second way, like where we have the knowledge, after all, like, for this exercise, you got the full RTL, so you can see what's inside the design. So one of the side notes is that, a lot of time designers don't put good comments, so it's very hard to read their designs, right? So as a verification person, I will highly encourage you to get in the habit of writing notes in your code as you go, right? So very, very important things which will help you. Just to give you an idea, like, I started my career in late 90s or mid 90s, and then till date in Intel, I can go to certain files and which will have my name written, because I will put my name and then some comments about my design. So if you put your names and your comments, names are not necessary, like as ethics, like nowadays people don't put names, but the comments will live forever in your designs. Like, after 20, 30 years, you will look back and say, oh, I wrote that comment, right? So, and it's helpful to the designers, they can just pick it up, or in our case, it's verification that they pick up your component, which you developed 20 years ago, and they can see your comments there, right? And they will feel happy. I've received calls from engineers asking me questions. I'll say, I don't know what I did back then, right? So, all right. So going into the design, if you look at it, this tiny ALU has two operation engines. The first one is single cycle engine, and second is the multi-cycle. Single cycle does certain operations and give the results in single cycle, as the name says. Whereas the multi-cycle takes 3 clocks to do multiplications and give the results out in 3 clocks, right? So based on the operation, one of these operations is selected, and then you mux the results into output, and that's when the done is asserted. Right. So now you looking at the design, you have more knowledge about that. Hey, I have within the design 2 different kind of operations, and that gives you more visibility or more thinking about how I'm going to validate these individual pieces, right? So now looking at the design, it's can people see read it like in the back? Or it's a little bit hard to read, but I could open the file and we can look at the code as well. So in our case, like what I've done is I put the whole design under test into one Verilog file. It's called design.db. And this is basically referencing to our UVM books, chapter 1 example. So I just want to put the credit where it is due. Looking at the module, there is a tiny module A defined, and then there is a module for single cycle operation, and then there is a module for 3-cycle operation, right? So those are our modules inside our DUT. And as you can see that tiny ALU at the top level has all the input and outputs instantiated. And then it does assign your start and done signals. And then you are assigning those components to these single cycle and multi-cycle modules, and sending those A and B and OP and all the input and output signals to each of these modules. And then you are implementing the behavior of done signal and result signals, based on when the signals are done, you can send those outputs on the output pins of this DUT. Inside the single cycle, all it is doing is a single cycle operation, and there are only few ops defined which are doing single cycle operation. It could be add, and operation, or operation, right? Multi-cycle, in the first cycle, you're doing first level of multiplication, second cycle, you're doing second level, and third cycle, you're doing third cycle. right? So our design is pretty straightforward, right? Like, so now as a verification engineer, you have to verify this design, right? So as a first exercise, anytime you will start working on a design, you will have some meetings with designer, discuss what his design is doing. You will meet the architects, get the specifications, understand what the specifications are. So that's where the black box and white box testing will work in the real world also. This white box wise, you'll start with architecture specs that, hey, what is the behavior of this design and testing going to be? You get those from the specs, you read those specs, and then start planning out your verification. Then you go into details, you go to the designer, meet with them, and understand the design a little bit so that you have some idea of what's needed. What designer will tell you is the pieces which he's worried about. That, hey, these are the pieces I want you to test, which I haven't tested. Or he may have done testing, or he may not have done testing, he or she. So based on that, like, you will figure out your verification strategy based on deeper knowledge of the design. Now, going into our methodology bucket, like we talked about building the verification environment and test bench. So you will come up with a plan that, hey, I have my design, I will build my test bench, I will use a simulator and check for the results, right? So you will make some decisions about, we decided that our environment will be Linux based, we'll use Mentor Questa for running the simulation, and this test bench is going to have all the components we discussed today, right? And for the ease, the code I provided for testbench.sv that contains all the components we have. Then you will see some code about coverage. We talked about coverage. So coverage is two types. By the way, as a disclaimer, I will be spending more time on coverage in next class as well. So for now, just understanding that scan through the code, you will understand. And just as a poll on the bridge, can people put, if they have some knowledge about coverage, how to code it? So I will like a response on the bridge about the coverage experience, or do you want me to cover it in more details in the class? Okay, so there are responses. What about in the class? Do people know what the coverage coding looks like? No? Okay, so I'll spend some time in the next class. That's why I wanted to take a poll so that I can prepare accordingly. Even though this class is supposed to be UVM, but as part of verification, I'll try to cover that a little bit. So code coverage, there are two types of coverages, code coverage and functional coverage. Actually, there are multiple kinds, but we are going to simplify it and just talk about those two. Code coverage is just looking at the code, has my test vectors toggled every line of my code, right? Like that's what code coverage is about. Is every line in my code been exercised? When I say that every line, what it means is mostly like design you'll be synthesizing. You want to make sure everything which is going to get synthesized has been exercised as part of this code coverage. Functional coverage, on the other hand, is you are looking for operations and figuring out, are those operations in the design being done, right? Like for example, you may test that, hey, I have done the AND operation, but the AND operation can be done with a lot of vectors, different vectors, right? So that's where the functionality will come into the picture. And then you will be executing operations after the reset, run a multiply every single cycle, run a single cycle operation after a multiply. So you want to do back-to-back single cycle and multiple cycle multiplication in this ALU. You want to simulate all the operations twice, right? And simulate all the zeros, simulate all the ones, right? So that's the coverage which you will see in the code being defined for this exercise as an example. And then we are going to use constrained random stimulus. I'll talk about constrained random stimulus a little bit more through the example of the code. So constrained random stimulus is a very important concept where when we generate the stimulus, again, do we want to generate all the vectors possible for a design space, or do we want to if we take random approach, like, where I'm randomly generating all the stimulus for my design, constrained random brings in some knowledge about the design. That's where the gray box testing comes in picture, where you have certain knowledge that I know that certain random spaces are bogus, they'll result into vectors which are not applicable for my design. So you can use constrained random approach where you can define the random vectors which are going to have more productive results. And we'll look at what it means in more example through one of the examples I have later on. And finally, it also has checker which has scoreboard, which will track for checks in this example. Now let's quickly look at the test bench code itself, right? Like starting with variable declaration, we have enumerated all the operations, and then we have instantiated a DUT with all the input and output pins here. I talked about the coverage. I think this may be repeat, like where we are going to cover for making sure we have defined multiple cover groups. Like, let me just go to the code directly. So one of the cover groups is which makes sure that all the operations have been tested, right? Like I have single cycle operations, I have multi-cycle operations, I have operations after the reset, reset followed by the operation, and operations after the reset. Then I have back-to-back single cycle multiplication, I have multiple cycle multiplication, I have two operations back-to-back, I have many operations back-to-back, right? So in a cover group, you can define what kind of sequences you want to cover in your design and observe that whether my verification has covered those or not, right? So this is a very specific example, like it has no requirement as such, but a designer will tell you that, hey, these are the conditions I want to make sure get tested in your design, right? Like, because if those conditions are stressed, it may expose some bug in my design, right? Like, so you will write certain coverage points yourself, and then designers can give you inputs that, hey, can you focus in this area where I'm a little bit concerned that there may be bugs hiding in my design, right? So cover groups can be targeted for certain sequences of operations, and you can make sure that those sequences are met. This is what we mean by functional coverage, right? So this ALU covers that as a cover group. Then I have initial blocks in my test bench where you're generating the clock. Usually the clocks for a design are supplied by the test bench. In this case, it's a single clock design. So we are just applying that clock, and it's toggles every 10 cycles or 10 nanosecond or whatever time you pick. Nowadays it's picosecond, so it will be in picoseconds. And then I have operations zeroed out, like, so I have this new constructor in system Verilog. I think you might have learned about constructors, and you will be defining initial values of the samples which are supplied. Then there is a tester block in our test bench. So this tester block is what is interacting with the DUV, right? Like, so this tester block is initializing the DUV, like supplying the reset and clocks. Then it is generating the test cases and sending those stimulus to the design, right? So this is a very simple example where we are not putting drivers and this and that. So this one tester block is doing all those functions, right? So this tester block generates 1,000 test cases and drives the test to the test to your DUV. And this is the code for it. Like, you are driving the reset. So basically the start and done signals, they get set as well, right? So at the beginning, your start is going to be 0. If there is a reset, then also the start will be 0. And after the done signal, you also drive the start to be 0. And then you are running 1,000 times your test on negative edge of the clock. So every negative edge of the clock, our operation set is getting the get op operation, you're getting the values for A and B. So that is done by these functions, get data for A and B, and then you keep doing it in 5,000 times, right? And looking deeper into this, your get ops and get data, which we talked earlier. So get op and get data. This is where the random constraint testing or concept will be explained. So what we are doing in get op is we have set of operations, right? Like if it's a 3-bit vector to have an operation choice, what operation you want to generate. So you can generate 8 values. So if you just throw a random number, it will generate 8 values. And those 8 values, based on those values, what operation will you send? How do you decide that, right? Like, so in a constrained random, what we are doing is instead of randomly generating operation, we can specify that, hey, most of the time, if you just glance through it, I'm sending no op twice. Like if the value of my random variable comes out to be 000 or 101, I'm sending no op, right? I could have sent AND twice, or I could have sent XOR twice, right? And then for 110 is 111, I'm sending the reset ops, right? So this is example where even though I have randomly generating these vectors, I can target them to certain exploration space using this technique. So this technique is called constrained random testing, right? It's a simple example here, but this is a very powerful technique, like where using random variables, you can target your tests in certain area to expose more. Here is yet another better example, like, get data. This looks very simple, but concept is very powerful, where you will see that I can generate sending random data with the operation is the most obvious thing, right? Like I want to test AND operation. I'll just send 2 random values of AND and see if it works correctly or not. But that's not how you test. You want to test what is the behavior with 0, or what is the behavior with 1, 1. If one of the operand is always 0 or always 1, then I get more interesting results. Don't you think so? Right? So as a tester, what you want to do is you want to generate those more than other values of data. So constrained random will do that. Like, I can define that, hey, I'm getting the values of random. If the value comes out to be 0, then I drive 0. Other cases, I drive 1s. And so what it will do is at least 2 of all these 4 conditions, you'll be generating 1 or 0, right? So using that constrained random, you can kind of target your tests to certain behavior. So that's the concept of constrained random testing. And then finally, I have coming back to our tester block. So I'm driving my tests. So this is looking at whole thing together. So initially, I initialize my test bench, drive the clocks. I am getting my operations, getting my data for A and B, and then I assert start, right? So the start is sent, and then after certain clocks, when I get the results, I can drop my done signal. Right. So you can look through the code, and this is what the tester function is doing here. And here comes the scoreboard, right? Like, so now I have injected my stimulus into my design. Then I have this reference model. We touched on reference model in our explanation earlier in the book. So here is the example for that. I know what a addition operation is. I know what a AND operation is, or and multiplication. So my reference model is pretty simple. Like I can just code it as a reference code in my scoreboard and let the design do whatever way you have implemented and compare your results to this reference model. Correct? So this is what scoreboarding is, that design is doing whatever they want. I want your results to match this reference model. So that's what scoreboarding is. So we create a simple scoreboard, and it has a predicted value. And if the predicted value doesn't match with the result I'm getting from my DUT, I'm going to throw an error. So this is an example of checking also that, hey, I asserted, as soon as it will see some problem, it will just flag it. Okay. All right, so this is your assignment number 1. It's very simple assignment where you just take this code, set up your environment and run this. And if you find some bugs, you fix those bugs. Right? So I want you to take this example as a very simple example to explain the concepts we have discussed today. And this will be my style for future lecturers also, where like as we go into UVM, we'll take some concepts and some code to work together with it. All right. Yes.
Is the random system Verilog, is that seeded or unseeded? Will it produce the same random values every time? Or
Yeah, it will produce same random values. So this is like very simple random functions. You bring up a good point. You know, creating a random number is also an art, right? And in verification world, it plays a big role, like, you know, because for reproducing a failure, there have been cases like, you know, where you run a test for 10 days and one bug shows up and you had a random environment and now you want someone to debug. In order to debug, you have to reproduce the results. And if you don't have the same random seed, you will get a different result, right? So it plays a very big role into constrained random testing. Good question. Any other questions? All right. So now we'll go into the concept of, so that was your assignment, I think problem number 2. Problem number 3 will be about reuse methodology, right? Like, so I'm giving you a monolithic one file test bench, and your job is to separate the components into BFMs and rewrite the code so that it becomes more reusable, right? So now we have created all these components, right? Like we created scoreboard, we created checkers, we created stimulus. As a verification person, once you write it, you want to reuse it. Like, for example, the way I wrote or provided you the code, it's one file. And if you want to reuse, how do you reuse, right? Like you can't use that scoreboard or you can't reuse that checker, right? So in order to do that, solution is pretty simple. Like you write them into different files so that in some file I can instantiate the checker, which I wrote for this file, right? For this design or this verification environment. Right. So this exercise talks about bus functional models. Like, so so bus functional models are written to increase the reusability and write your verification into more modular fashion. So basically, like we wrote coverage is repeating the same things. Like, you know, we wrote a self-checking test bench. And we want to ultimately rewrite the code so that we can develop it more like a BFM. And there is a solution also there. Like, again, the exercise here is to understand the concepts rather than worrying about, you know, how to write it. So the way it will be written is like at the top level going back, the code size will reduce in each file. We have created the tiny ALU BFM. So you will have a BFM, which is the top level test bench BFM. And in that test bench, BFM, you have a tester, you have a coverage, and you have a scoreboard, right? And then you instantiate this BFM to the DUT. And the way you are doing it is you take the DUT pins and apply to the BFM pins, right? So that this becomes your short top level test bench as compared to the one big monolithic file. Now looking inside individual BFM components, right? Like, so inside a package, like we have enumerated all our operations. And then if you look inside the tiny ALU BFM package, right? Interface is going to be same as before, like before as you had for the test bench. And then you have other blocks like, you know, it's also going to take care of the clocks, generating the clocks for the DUT as well as for the test bench. And then it also takes care of the reset functions, right? So it's taking care of the environment functions, which will make your design as well as your test bench run or tester run. Because what we have done is we have separated out the tester, which is the heart of your tests and stimulus and things, right? So we have separated that out and created a simple BFM as a driver, which is taking the stimulus and driving to your design. So here is the remaining code here, like, this is how it looks like. So you are first resetting, then you are creating some no operations and all other operations you're sending those. So you can walk through the code, like I don't want to, because of the shortage of time, I won't go into too much details. If you run into any problems as you go through the code, you can always ask me later on or in the next class. We are defining clock tasks, we are defining reset task and the send off, right? So ultimately our ultimate goal is to send the stimulus to the DUT, and these are the code sections which have been highlighted in the class material. And scoreboard and the stimulus, right? So coverage pieces, like let me touch on it a little bit. And as I mentioned, we'll cover coverage more in next classes. So coverage also, like coverage is being written as one component of this BFM approach. And but the concepts are same as the monolithic one, like where you are defining different coverage groups for the design requirements we had defined earlier, right? Like we had said, designer wants to see this covered. So we have written that as part of those cover groups, which you will see. And in this BFM approach, it's same code, just sitting into the tester file. All right, so that covers the third portion of the homework assignment. And any questions on this as well? Thank you.
I'm unfamiliar with this cover group syntax stuff. Like I feel like conceptually I understand what coverage is, but I have not personally ever interacted or seen this syntax. Are you able to like maybe give a quick explanation of some of what's going on here?
Yeah.
Bins,
Yeah, as I mentioned, like next class, I'll go in more details.
okay, do we not
So,
need to know
for this assignment, you can just take the code as it is. I'm not asking you to change coverage or anything.
okay.
So you can just take the code as it is and go with it. Let me see if I can zoom in. It's hard to read. That's why my eyesight is poor. Let's see. Zoom in there. Right.
Yeah, and of course I can like Google some of this and look at.
No, I can quickly, because we have time, like we are ahead of schedule. So we are defining different cover groups, as I mentioned earlier. So there's one cover group defined here, which is called op cover group, and there's a second cover group defined as zeros and ones cover group, and there can be multiple cover groups defined. And what cover groups do is, like, as they print the reports, they will just put it into one report together. And within this cover group, we are defining cover points. So there's a cover point being defined. We'll discuss that in more details. And then within that cover points, like we have bins defined. So bins is a collection of certain operations, and these bins are single cycle bins, multi-cycle bins. And if you look at the syntax, what it is for single cycle, it looks at either add operation or a XOR operation, and followed with reset operation and move operation, right? Multi-cycle is looking at just the multi-cycle operations, and this one is there will be a concept of blocking and non-blocking. What this syntax means is you have one of these operations, add operation or multiply, followed with reset operation, right? And in this other case, you have reset followed with add and multiply, right? And you will see same syntax being used at all these places. There's a new syntax here, like, so what this means is you are seeing a add operation or multiplication operation twice, 2 times. like back to back, you have to do operations.
And it'll, like this, the bins variable name, it'll have like the count that occurred during.
Yeah.
the test.
Yeah. So when you will run this test, that's the exercise you have. You're supposed to submit the log file, and in the log file, you will see the coverage reports. Yeah. So basically these coverage reports will say that, hey, how many times in this run you saw this bin filled, like how many times this bin was filled. Right? So same thing here, like, we have some cover points defined and the bins, right? Like, so these bins are.
The syntax is just throwing me a little bit because it looks like concatenation or I don't know. About it.
No, there's no concatenation at
Yeah.
all. Like, yeah, so
You know,
yeah.
From the design side, like the curly braces that you like X68.
Mhm.
Okay, and so this isn't actually forcing any stimulus. This is just keeping track of how many times I saw a reset operation followed by an add.
Exactly.
Okay, and then we can get a good idea of we covered everything or we
Yes.
covered this, but not that.
Yes, exactly.
Perfect.
Perfect.
Thank you.
Because we emphasized in the first part of the lecture that when verification is done has to be known, right? Like when you take this report to designer and the verification manager, they'll say that, hey, now I can see what is being covered, what is not covered. And they'll say, hey, the coverage here is low. You need to generate more tests in this area, right? Or they may waive it. They will say that, hey, it's not that important. Let's not waste time on this and let's just move on. Right? So coverage tells how much testing has been done, right? Otherwise, like, how do they trust you? Like they'll say, oh, you gave me something and I tested, I'm done.
Got them.
Yeah, no problem. Right. So this is a more tangible way to produce that, right? Okay. Use it back out. All right. So next class. So what I'm doing is like I'm trying to build the basic concepts for you. Then we'll go into the tough part, which is the language part. Like System Verilog is a big space. So I'm trying to focus on some items which will be important for UVM ultimately, because my goal is to, when you walk out of this class, you're expert of UVM, right? So UVM has concepts of object-oriented programming, right? That's another poll I will just take right now. How many of you have done like some C programming or some object-oriented programming? Okay, that's a large number. What about on the bridge? Can you write in the chat if you have experience with object-oriented programming or C? Okay. Yeah, looks like this should come easy for everyone, right? Like, so next class, what we'll do is like these concepts of verification methodology, we'll build on it to go towards UVM, right? So we're starting with a simple System Verilog ALU test bench, and then we'll slowly morph it into a UVM test bench over the next couple of classes, right? That's why like I picked a very simple design, very simple test bench, but let's focus on the concepts for the first few classes, right? And as a project, you will be deciding what project you want to do, but if you pick this one, then again, you will be just working through the class to add a cache controller. Hard piece will be finding a cache controller, adding that, things like that, like, but other than that, like it should just build over the classes. If you pick a different project, we'll take the same approach, that concepts you learn in the class, you can start updating your test bench, and those will be your homework assignments over the next few weeks, right? So I will spend time giving the more conceptual coding for coverage and some of the coding concepts. I will also cover object-oriented programming of System Verilog because that will be used with UVM. UVM comes with its own class library, but the concepts are, they have to work with the design also, so you have to know a little bit. And then we may touch some of the verification methodologies from today, which will go into UVM. Okay. So should I hold you for 10 minutes or should you guys want 10 minutes back in your day?
I think the class ends at 6:30, right?
Oh, it ends at 6.
Yeah.
Ah, they're on time. Okay. All right. Wonderful. Any questions on the bridge or here in the room before we close the day? Okay, silence means everybody is happy. They want to go home. All right. Thanks, everyone.
Thank you, Professor.
Thank you, Professor.
Thank you.